So let us see what we can achieve by using quantum effects, and for this we start with some preparations. Well, we are going to use superpositions. And we are going to use entanglement. And our method to generate superpositions is using Hadamard gates. So when we act with a Hadamard gate on a single qubit in this state, we obtain this superposition. And when we act on the other computational basis state, we obtain this superposition. And when it comes to a system with many qubits, we had already established when we apply Hadamard gates to all of them, and I'll just write this as a product of Hadamard gates here, and say we apply this to the state where all the quantum bits are initially set to 0. Then we obtain a superposition of all the computational basis states, and I will enumerate these now by an integer z, running from 0 to curly n minus 1, and this will then be normalized by a factor 1 over root curly n, which indicates that all of these computational basis states now appear with the same probability. So this is a state which we denoted as capital psi. And what I want to do now is to also remind us of what happens when we apply all these Hadamard gates to another computational basis state that I call x. And this is a state which can be written in terms of binary digits, such as this. And this we can then do by applying all these Hadamard gates bit by bit. So again, this is something which we have done before, but it's really worthwhile to have another look at this, because this will now be superpositions of zeros and ones for each of the states. But whether we now obtain a superposition with a plus sign or a minus sign now depends on the corresponding value of the bit in this sequence here. So here we encounter a plus or a minus sign that we can write as -1 to the power xn for each of these bits. And then we can multiply this out and write this as a sum over all the computational basis states. Z running again from 0 to curly n minus 1. And in front of this we will sometimes have a +1 or a -1. And we will pick up minus signs whenever xn is equal to 1 and zn is equal to 1. And this can then be written as this bitwise product between x and z. So this sum here, where we sum over all the different positions of these bits from 0 to n minus 1 and multiply the bits at the same position from these two integers. So this is really a recapitulation of results that we'd already established before, but what I want to emphasize here is that we found a way to put plus or minus signs in front of the different computational basis states and therefore change the way that these can interfere. And here we have achieved this depending on the value of x, which you can view as an input. So the question is whether we can also achieve this for outputs of functions f of x. And we can indeed do this by using entanglement and function gates. So let us recall what a function gate is. And we are going to specify this for the case that this is a function which can have an input with multiple quantum bits. But this output we are just going to restrict for the moment to a single quantum bit. And the way that this is generally achieved by a function gate is to retain some memory of the input and change this output by just adding the result of the function modulo 2 to this lower bit here. And this is really specified in the computational basis. But what is really interesting is when we select a certain superposition for y. So let us set y to this superposition here. Which is the superposition that you obtain by operating with the Hadamard gate on this state here. So this is now no longer a computational basis state, but it is of course still a superposition of such, and therefore we can still work this out, and it is really instructive to do this step by step. So here we still have x, and down here we now have this specific state. And when we feed this now through the function gate, then we have to add f of x to these bits. So here we obtain 1 over root 2 times f of x. And here we can write this as 1 over root 2 1 minus f of x, indicating that this changes to 0 exactly when f of x is equal to 1. And now this result can be rewritten in a very instructive way. Namely, when f of x is equal to 0, so if we have a 0 here and a 0 here, then we just return to our original state. But when f of x is equal to 1, then here we have a 1, and here we subtract this 1 to obtain a 0, and this is the same as interchanging the position of the 0 and 1 in the original state, but these here enter with this minus sign, so this is the same as putting a minus sign just in front of the whole state. And therefore all of this can be written very compactly in the following form. And all the while this state here has of course not changed. And our final quantum state of the complete system is simply the product between these two outputs here. But in this product it does not matter where we put this factor here. We could just as much put it in front of this state here. So the result can also be rewritten in the following form. And when we now look at this, we see that the role of the two quantum bits has been interchanged. The second quantum bit always remains in its state in this superposition here, while the first quantum bit can change its state, namely it picks up a minus sign whenever f of x is equal to 1. So this reminds us a little bit of what we achieved earlier when we had a controlled NOT gate and placed Hadamard gates around this to transform this into another controlled NOT gate, thereby effectively interchanging the notions of cause and effect. And just as there, we here made use of a superposition produced by Hadamard gate, namely this superposition here. Now this is a very common element and mechanism that we are going to employ in some of our quantum algorithms, and therefore we are going to give it a specific name. We are going to call this the marking of a state. And what we mean by this specifically is that we mark these computational basis states with plus or minus sign depending on the value of the function f of x. In particular, we will utilize this marking of states in our first quantum algorithm, namely the Deutsch algorithm. The purpose of the Deutsch algorithm is to make statements about a certain class of functions, very simple ones, where the input is just a single bit and so is the output f of x. And we had already discussed that such functions exist in 4 different variations, which we can all enumerate by indices, which just reflect the corresponding outputs. So these 4 functions here, for which the outputs are just given by these values here. And at the time when we first encountered them, we emphasized that 2 of these functions are reversible and the other aren't. And the ones which are not reversible are indeed these 2 functions here, which mathematically we would call constant functions. While for the other 2 functions, the outputs 1 and 0 both appear the same number of times, and these type of functions we call balanced functions. And when we want to distinguish the constant from the balanced functions, we will have to look at both of the possible inputs and compare the outputs. So we ask the simple question, Are these two outputs the same? Or do they indeed differ from each other? So to distinguish whether a given function is constant or balanced, we have to evaluate it twice. But the Deutsch algorithm achieves this distinction by using the corresponding function gate only once. And it does so in the following way. We place our function gate, implementing the function in question, which we assume to be unknown, into the middle. And then we place Hadamard gates around it. And in particular, two Hadamard gates here at the front and one Hadamard gate here. At the end, we will do a measurement on this quantum bit, so just a single readout. And this will determine whether our function is constant and balanced. So what happens to the second quantum bit will actually not be important, but it is convenient to feed this also through a Hadamard gate, which will simplify our final results and make the interpretation a bit more transparent. But this Hadamard gate down here, this is really not essential, so this could also be omitted. And now we still have to specify our initial quantum states, and we will start from computational basis states, namely the state 0 for the first quantum bit and the state 1 for the second quantum bit. Now we start with the state 1 here, simply because at this place we then have the superposition 1 over root 2, 0 minus 1. So this odd superposition that we just encountered in the process of marking states. And we start out with the state 0 above, so that we obtain here this superposition, the even superposition, so that we are testing this function gate now for both of the possible inputs. And now, given that we already discussed the marking of states, we can immediately write down what we have at this place here. Because at this place, our states are now just marked by the values of the function for the corresponding inputs. So this is our result. And there are basically two cases when f of naught is equal to f of 1. So this is for a constant function. Then this state here will be proportional to the even superposition. And in the case that they are not, then this state there will be proportional to the odd superposition. So on top of this we have these factors 1 over root 2 and possibly an overall minus sign in front of all of this. But the overall minus sign does not change any of the probabilities, and the factor of root 2 is just for normalization. What is essential is that when we feed this state through this Hadamard gate at this place, this state here will become the state 0, and this state will become the state 1. And therefore our output here will be just 0 in this case and 1 in this case. So we have used our function gate only once, and we have now one output bit, and what this output bit tells us is whether this case applies or this case applies. But the first case is of course just the case of constant functions, and the second case is the case of balanced functions. So just as promised, this Deutsch algorithm achieves this distinction by a single evocation of the corresponding function gate. And what we have utilized are of course superpositions, where we fed both of the possible inputs into the function gate at the same time. And on the other side, these states were marked by the corresponding outputs in terms of plus or minus sign as specified here. So here we utilize superpositions, or what we physically would call interference, namely constructive or destructive interference, depending on the signs that we have picked up here. And to see how interference really enters this whole process, it is useful to consider the following physical implementation. Let us consider objects that can reflect light, but they do so depending on two possible coatings. We have one type of coating for which the light is being reflected without a phase shift, and another type of coating for which the light is being reflected with a phase shift of half of its wavelength. And now we consider a collection of objects where some of them have the same coating on both sides and others have different coatings on both sides. And by utilizing interference, we can now distinguish between these different types of objects by just using a single photon. So we send the single photon first through a beam splitter, which means that it can be transmitted or reflected, and we say that this happens with equal chance. So 50% probability for transmission and reflection. And then we direct the photon towards our object so that it is reflected with a phase shift which might be 0 or lambda over 2. Next we have another pair of mirrors, and these direct the photon onto another beam splitter. And at this beam splitter, the photon will be deflected into two possible directions. And there we place photodetectors, so one photodetector here and another one here. But at which of these two photodetectors a photon will arrive depends on whether we have constructive or destructive interference at this beam splitter here. So let us assume that this is the direction in which the photon travels whenever we have constructive interference, which is the case whenever the phase difference between the two different paths is a multiple of the wavelength. And this now occurs whenever the two coatings on these objects are the same, because either we have no phase difference from both of them, or we have a phase difference of lambda over 2 from both of them. So in both cases, the phase difference is the same. So this photodetector would be triggered whenever we have physical objects with the same coatings on both sides. But whenever we do this with an object that has two different coatings, then we have a path length difference of lambda over 2 and therefore destructive interference. So we are deflected into the other direction and trigger this photodetector here. So this photodetector is always triggered in this case here. So we indeed managed to distinguish between the different types of objects by just a single photon using interference. And this is not just a physical analogy, it really translates also mathematically into this quantum circuit when we identify the states of the quantum bit, for one with the two different types of polarization for the photon, horizontal and vertical, and secondly also with the two different ways that the photon can travel through this device, namely using the upper or the lower arm, including the possibility that it might have arrived initially from this direction here. So at every stage, the photon has two different directions of polarization, as well as a choice to travel through this part or this part of the device. So at every point, there are really 4 different states, which correspond to the 4 computational basis states of 2 quantum bits. And in this physical implementation, which is spatially completely symmetric, we indeed realize this circuit, including this extra Hadamard gate here, whose only purpose is to transform the state of the second quantum bit back to its original state. So this computational basis state here. And this is simply for convenience, because our calculations tend to become simpler when we not only start, but also end up in such computational basis states. So this is our first example of a quantum algorithm that answers a certain mathematical question in fewer steps than possible in the classical setting. Next, we are going to generalize this to the so-called Deutsch-Jozsa algorithm, which is still concerning constant or balanced functions with a single bit as an output, but there the input can represent many bits.